gentlemen, will you please take your seats so we can begin today's conference? I take a great deal of pleasure in presenting to you today as our guest speaker, Dr. Wernher Von Braun. Dr. Braun.
Gentlemen, the conquest of outer space is the greatest technological challenge of the age in which we live. The first decisive step in the conquest of space will be the placing of an object into an orbit wherein it will indefinitely circle the Earth. It takes a speed of approximately 18,000 miles per hour to accomplish this. And this is approximately 3 times the greatest speed ever attained by rockets today. How can we reach such a speed? First of all, of course, one could think of improving propellants used in present-day rockets. Secondly, we could shave some weights off our designs. But with both these methods, it does not appear possible to gain more than approximately 40 or 50% of the speeds that rockets reach today. A fundamental step ahead in increasing the speed will be the application of the multi-stage principle. Let us take a look at our first slide. You see a model of a 3-stage rocket on this picture. Up to this lower white line here is the first stage. It is powered by a number of rocket engines which will lift the missile off the ground until it has reached, after approximately 1 minute operating time, a maximum speed in the order of 3,600 to 4,000 miles per hour. At this point, the first stage is jettisoned. Its tanks are now burned out, and the rocket motors of the second stage take over. The second stage adds a velocity increment of approximately 6,000 to 8,000 feet per second to that of the first stage. And after this speed of approximately 12,000 feet per second has been reached, the second stage, likewise exhausted, would be dropped. Now the rocket motor in the last or top stage will take over. This top stage will now forge ahead at an initial speed of approximately 12,000 miles per hour until the final orbital speed of 18,000 miles has been reached. This speed is sufficient to keep the top stage in the orbit. Now, what exactly makes an orbit tick? Imagine you put a gun on top of a mountain and fire it in horizontal direction. The gravitational pull of the Earth will pull the bullet down towards the ground, and after having traveled a certain distance, the bullet will finally strike the ground. Now, as we increase the muzzle velocity, the bullet will travel farther. And at a certain speed, the curvature caused by the gravitational pull of the Earth, which pulls the bullet down, will exactly match the curvature of the Earth. The bullet will then keep on flying around the Earth and will fall and fall, never being able to reach the surface of the Earth until it finally hits the breech of the gun from the rear. This is an orbit. You can establish such orbits at various altitudes. Theoretically, you could establish one immediately above the ground, but of course interference with the atmosphere would slow the bullet down and the orbit wouldn't be stable. So we have to go outside of the atmosphere. But once we are outside of the atmosphere, we have a free choice of any altitude we want. And the higher we go, the slower will be the velocity required to balance the gravitational pull of the Earth. For it is the centrifugal force in the curved orbit that cancels the gravitational pull of the Earth and keeps the object in its stable orbit. The Moon has been doing this for a number of million years, and the Earth is orbiting around the Sun, so the principle is well known and proven in Mother Nature's pattern of things. With such a rocket, of course, we couldn't return back from the orbit, and if we are thinking of shooting people into an orbit, we have to provide ways and means of returning them safely to the surface of the Earth. Here we have replaced the top stage of the rocket by a winged airplane-type stage which would carry personnel to the orbit. This winged top stage would attain the same orbital conditions as the non-winged version that you saw on the previous slide, but with the help of these wings, the top stage would be able to return to the Earth. This picture here shows the pattern of the track of ascent of such a three-stage rocket ship. The ship would take off vertically, and soon after takeoff, it is tilted into a slanting flight path so that after the 1 minute or 80 seconds of burning time of the first stage is over, the rocket would fly on an angle of approximately 20 degrees against the horizon. At this point, the first stage is dropped and the second stage takes over. At burnout of the second stage, approximately 2 minutes later, the travel of the rocket will be almost horizontal. We drop the second stage at an altitude of approximately 60 to 80 miles. The rocket has now attained a speed of 12,000 miles per hour, and the third stage now takes over until the final speed of 18,000 miles per hour has been reached. During this powered flight path of the third stage, the rocket would hardly gain any altitude, so that the rocket still is only about 60 miles up at the time cutoff of the last stage is reached. If the third stage would reach exactly circular orbital conditions, defined by the simple condition that the centrifugal force would match the gravitational pull, and therefore the curvature of the orbit would exactly match the curvature of the Earth, the third stage would then stay in a circular orbit 60 miles up. But if we provide a little more speed for the third stage, we have some excess velocity and excess centrifugal force, which would carry the upper stage, the top stage, even further away from the Earth. The rocket would then go into an elliptic orbit, which after going halfway around the Earth would reach an apogee, whose altitude depends only on the excess velocity over circular orbital speed that we had at the moment of cutoff. We allow the rocket to continue through this elliptical trajectory. It would go back to the perigee, the lowest point, which was identical with the cutoff point of the last stage, and would stay in such an elliptic orbit again forever. Now when I say forever, I have to qualify this. Every time the rocket would go through the perigee, only 60 miles up, it would be retarded slightly by the aerodynamic drag caused by the traces of the atmosphere that are still found at that altitude. So every time it would go through the perigee, it would lose a little bit of that excess speed, and as a result, the next apogee would be somewhat lower. And this gradual loss in excess speed would gradually lead to a conversion of the elliptic orbit into a circular orbit 60 miles up. And after this has been accomplished, the ship would be subjected to atmospheric drag throughout the entire flight around the Earth, and from then on, of course, it would lose speed rather rapidly. But with the help of the wings, it would be able to land again. If it had no wings, it would descend into the deeper atmosphere, ultimately burn up and crash. During the ascent of such a three-stage rocket ship, the crew will be subjected to high accelerations. Of course, initially, as the ship takes off, the ship is still heavy, and the acceleration will not be too high. But as it loses weight due to fuel consumption, and with the thrust remaining constant, this acceleration will gradually increase. And the first peak in the acceleration curve will be reached at the moment of cutoff of the first stage. Since all the powerful motors, the first stage, keep pushing the ship, and the first stage tanks, which constitute approximately 75% of the total ship's weight, are almost empty. The acceleration peak at this point will be approximately 9g. It can be kept lower if desired, but only at the expense of a slightly higher fuel consumption. After this first peak, the acceleration will go down to about 1.5g again, when the smaller motors, the second stage, take over, and of course the second stage tanks are still full. The second peak will then be reached at cutoff of the second stage, again approximately 9g. And finally, another third peak of the acceleration curve will be reached at cutoff of the third stage, but it won't be quite that high because the third stage carries the payload, and in addition, if it's an Earth-returnable winged upper stage, the propellants required for the return flight. One of the most important tasks in preparing a crew for such rocket ships will be to make this crew work as a team under these harsh acceleration conditions. The tool to train teams for this condition is the centrifuge. Now, centrifuge, like the one you see on this picture here, are in use in the armed forces to check people for their blackout limits. By adopting the same principle and just making the nacelle at the tip of that centrifuge larger, we can place an entire crew into the nacelle and train them as a team. This is shown here on the next picture. We have an entire replica of the passenger nacelle attached to the boom of the centrifuge. And we can not only whirl it around and expose the men to acceleration, we can even rotate the nacelle as it swings around to simulate erratic flight conditions under which the crew must likewise take the necessary emergency measures. Let us take a look at the inside of this replica of the crew compartment during a centrifuge test. Here you see the men sitting one behind the other, exposed to the 8 or 9g acceleration and supposed to take the necessary emergency measures after an outside operator has portrayed a certain emergency situation on their dashboard panels. High accelerations are only one part of the problem to which the crew is subjected. Weightlessness, the opposite of high acceleration, is another. What causes weightlessness and when does it occur in rocket ships? You often hear that weightlessness is encountered only after a ship has left the gravitational field of the Earth. This is not true. Weightlessness in a rocket ship actually occurs the moment the engines are cut off and the ship is coasting freely and outside of the atmosphere through any trajectory, on orbit for that matter. What causes weightlessness? Weight as we know it is actually the cause not only of gravity but also of the floor on which we stand and which prevents us from freely following the pull of gravity. In other words, it always takes gravity and a rigid support to create the sensation of weight. As you withdraw that support and permit a body to freely follow the pull of gravity, that body is weightless. If you jump from a diving board into the water, you are weightless for a second or so until you hit the water. And if you are flying in a rocket ship that is not powered, your body is subjected to the same laws of motion that the ship is subjected to in which you travel. As a result, there can be no differential forces between you and the ship, and you will float freely within the cabin of the ship. Now, can we simulate weightless conditions on the ground? It is very difficult because usually any weightless condition is always terminated by an impact because it builds up speed if we do it in the gravitational field of the Earth. But there's one possibility of simulating it. If you look at this chart, you will see down here in the left lower corner the trajectory of an airplane that comes down in an inclined dive, then pulls out of the dive and goes through a ballistic trajectory. This ballistic trajectory is essentially a parabola wherein the aerodynamic drag is just compensated by the thrust of the jet engine of the plane. If you can steer the plane through this ballistic trajectory at zero lift so that you have no lift forces, and at the same time keep it on a proper course and just compensate the drag with your engine, you go through such a parabola. Of course, on the descending leg of the parabola, the plane will pick up speed again, and sooner or later you have to pull the plane out of the parabola again. But during that period, which in a modern jet fighter can be extended for approximately 40 seconds, you can simulate a weightless condition. If you would do the same thing with an advanced rocket plane, such as these modern rocket research planes, it appears possible to extend this condition to approximately 3 minutes. Under this flight condition through the ballistic trajectory, you have weightlessness. Such a long 3-minute weightless ballistic parabola is shown in the upper part of this picture. The next slide shows what happens inside an airplane flown through such a ballistic trajectory. You see a little matchbox floating in the left upper corner of the canopy. This matchbox was released by the passenger in this flight and was photographed by him to show that the matchbox is actually floating freely in the canopy, and it floated there for approximately 40 seconds. In fact, pilots who have repeatedly flown through such ballistic trajectories even use such free-floating objects to make sure that they are right under the weightless condition. If they apply a positive or a negative lift, the matchbox will come up and down, and if they have too little or too much thrust, so that they either under or overcompensate the aerodynamic drag, the matchbox will move fore or aft. This condition, which as I said can be simulated 40 seconds now and for maybe 3 minutes with advanced rocket airplanes, will be a permanent experience in any orbiting rocket ship. What will happen when man is subjected to this condition? Well, we know that a man can eat and drink even in a horizontal position, and if you try it, you find that you can even eat upside down. Will the blood circulation be affected? Medical doctors think that it will not, because the most important factor in the blood circulation is the drag, the resistance of the blood in the veins and the arteries. And gravity plays only a minor part in it. Well, in fact, you can lie horizontally in your bed and you can get up and your heart circulation is hardly affected. But nobody knows today how extended weightlessness will affect people. Some doctors believe the most critical question will be the sense of equilibrium in the inner ear. There's a little pebble in the inner ear, both inner ears, called the otholites, which rests on some hairs, and on whichever hairs they rest is an indication this is down. If you move your head forward, that pebble moves on another set of hairs, and you have a different indication of the plumb bob direction. Under weightless conditions, this pebble, of course, is disoriented and it simply floats without touching any hair, or may erratically touch a hair here and a hair there. And the question is, how will you react? The feeling is some people may get seasick, maybe they can get used to it. In these flights through ballistic trajectories, people have been trained to draw little sketches, and the interesting thing was that the sketches improved after going repeatedly through the experience. So all we can say today is that there is reasonable hope that people can be trained and accustomed to this unique condition of weightlessness. So you see, this weightless condition actually exists in a rocket flying unpowered outside of the atmosphere. Now what happens when our ship gets into the orbit? On this picture, we have assumed that the ship took off from an island in the Pacific and climbs into land under about 65 degrees to the equator. So the ascent is on a northeasterly course. Shortly after having left the island, in fact about 1,000 miles downrange, the last stage has reached terminal velocity. But since it has an excess velocity over and above circular orbital speed at that altitude, it now recedes further away from the Earth, unpowered, and reaches the apogee just 180 degrees on the right upper corner of this globe. If we want to establish our rocket in a circular orbit at this altitude, 1,070 miles up, we have to provide a little extra kick in this apogee to prevent the rocket from going down to the perigee altitude of 60 miles again. This is a minor maneuver requiring only about 15 seconds of power application. After we have given the third stage this extra kick, it is now permanently established in a circular orbit 1,075 miles up. This picture here shows the interaction between such an orbit and the rotation of the Earth. In a 1,075-mile orbit, the ship will go around the Earth once every 2 hours. But the Earth itself will rotate inside the orbit at a rate of 1 revolution in 24 hours. As a result, the orbiting station will pass the equator each time at a different meridian. And an observer in the ship will see different portions of the Earth overflown during a period of 24 hours. In fact, within a period of 24 hours, he will have the opportunity to see every point on Earth at least once. And this is one of the reasons why I believe that such a manned orbital station will have a terrific military importance, both as a reconnaissance station and possibly even as a bombing platform. It has been suggested to build a manned space station in such an orbit, 1,075 miles up, a 2-hour orbit. But before one could build such a station, it would be necessary to provide facilities or equipment so that people can leave their orbiting ship. Since the orbit lies in the vacuum of outer space, it would be necessary for anyone to leave the ship to don a pressurized suit. The man is essentially garbed into a fiber-reinforced rubber suit with flexible joints, and it is possible to walk with such a suit, although there is 1/2 of normal atmospheric pressure inside the suit. It is questionable, however, whether such a suit fashioned after the human shape is quite ideal for assembly operations to be performed in an orbit. In the first place, in order to build something, you usually don't need your feet, but only your hands. And secondly, you have to use quite complicated tools to do a decent assembly job in an orbit. For this reason, I believe that space suits to be used for such orbital assembly work may actually look quite different. The next slide shows what they might look like. This is actually no longer a suit. It looks more like a Coke bottle. It is a rigid container which is pressurized inside with the man looking out through a glassed dome at the top. The operator would be strapped to a kind of a couch inside this bottle and can turn himself around within the bottle. In front of him will be a whole panel of instruments through which he can operate these artificial arms that you see sticking out from the bottle. The arms can be retracted, and at the end of each arm can be a different kind of tool. It may be a hook, or it may be a drilling head with various gauge drills, or there may be pliers or wrenches and so forth. The entire system would be fashioned after, shall we say, the method of operating amputees' arms. The man could move himself around by built-in gyroscopes, which he can control with a steering stick, so as to acquire any spatial attitude he wishes by just using the precession forces of the gyros. There will also be 2 small rocket motors, one on top of his canopy, and the other at the bottom of the bottle, which could be used for transversal motion. The thrusts required would be only in the order of a few pounds. With such equipment, we could seriously think of assembling an orbital station. Now, what will such an orbital station look like? I don't know. Maybe it is smarter to build a number of small ones. Maybe we want to cramp a lot of equipment into a large station. This is immaterial. On the right side of this picture, you see a large wheel-shaped space station, which should be construed more or less as a proposal as to what you could possibly do with a space station, and it is not necessarily a proposal that a space station must look exactly like the thing, in particular must be that large. In fact, it can be a lot smaller if you want to reduce the equipment aboard or prefer to have several smaller ones. The wheel shape has been chosen for the purpose of doing away with the permanent weightless condition prevailing in the orbit. By putting a spin on such a wheel, you could provide an artificial or synthetic gravity in the rim. The wheel would simply spin slowly about its hub, And by putting the right spin on, you can either simulate 1 g acceleration in the rim or 1/3 of a g if that's considered sufficient. At any rate, you can give people their weight back. The people, of course, would live in the rim. Now, how would it be possible to build such a large station in an orbit, and how could we bring the equipment up to do this? The cargo holds in even large rocket ships will always be limited, so one of the most important things will be that you can ship the parts up small enough so they can be stowed away in the cargo holds. One way of doing it would be to fold them together. And in this particular proposal, I had envisioned to build the space station of 10 or 15 segments of rubber impregnated fiberglass or some material similar to that used in rubber floats or rubber rafts, and put the ring-shaped space station together from these sections. After the assembly has been completed and all the sections have been joined together, the entire unit can be inflated like an automobile tire, and this would provide not only the necessary rigidity to the structure, but also the atmosphere within the tire in which people could live. Of course, for an extended stay, it would be necessary to replenish the air and provide an air conditioning system, an oxygen replenishing system, and CO2 removal system in the station. Inside, such a space station may contain all sorts of equipment. There will be laboratories in the rim where phenomena can be studied which are not accessible to experimentation on the ground. Such experiments may include questions involving biological and zoological life under the conditions of outer space, cosmic radiation, meteorological research, whereby the Earth can be observed from the outside, astronomical laboratories, etc. Close to the space station, there will be a powerful telescope. If you aim this telescope at the heavens, you can see the planets unblurred by atmospheric effects, and we can expect to be able to take photographs of planets like Mars or Jupiter with unprecedented clarity. If you turn the same telescope to the ground, you would be able to distinguish as much detail as you can see from a plane, say 4,000 or 5,000 feet up. This, of course, offers tremendous possibilities to reconnaissance, and both reconnaissance in the civilian sense as in the military sense. The civilian reconnaissance, I mean iceberg warnings could be flashed to ships, expeditions could be observed as they proceed over the Arctic plains, and military reconnaissance, of course, means that you could keep a watchful eye on countries not accessible with aerial reconnaissance aircraft. As far as the military's application of the station is concerned, it seems even feasible to use such a platform in space as a base for the bombing of objects on the ground. And it is my opinion that such bombing could be carried out with an unprecedented accuracy from such a station. The most important application of a space station, however, will be that it can serve as a jump-off basis for trips into deeper space.